This is Algebra 2, Lesson 4.5 on exponential and logarithmic equations and inequalities. And we will be using the log properties that we learned in the previous section in order to undo and thus solve these equations and inequalities. And we have another lame math joke. The teacher, did you get the answer? And the student, well, I got closer and closer to it, but I guess it was just an asymptote. Okay, vocabulary, pretty straightforward. And the first example. So here we have an exponential equation that we are going to solve. And for this particular one, the easiest way to solve it is going to be, well, because 8 and 2 are both of the bases, and they can both be written with base 2, that's going to be the fastest way to solve this probably. So the 8, I'm going to rewrite with a base of 2. So 2 to the third is 8. And then it's still, the 8 is being raised to the x, so I still need to have it to the x. And then the other side is already base 2. So the goal is to get the bases identical. Then on the left I'm going to use a exponent property. When you raise a power to a power, you multiply the two exponents. So that's that property, a to the m to the n is a to the m n. So we get this, set that equal. And as long as I have two exponentials set equal to each other and they have the same base, then that means their exponents have to be identical. So therefore 3x has to equal x plus 6. And then we can solve that. We can subtract x from both sides, so you get 2x equals 6. Divide by 2, x is 3. And then these, you should check them. Some of the equations we're going to do today you have to check. Oh, so we'll do a check here. Actually, I'm going to go back to the original, sorry. So go back to your original in order to check it. So we've got 8 to the third equals 2 to the 3 plus 6. Okay, 8 to the third, we'll go to the calculator. We maybe don't know that off the top of our head. Okay, it's 512. And then this would be 2 to the ninth, and I do believe that is 512. So yes, 512 equals 512, it checks. Okay, so we've got base 5 on the left. Can we rewrite 200 as 5 to a power? Well, you can guess and check and try, but there is nothing that you can't raise 5 to a power and get 200. So we are not going to be able to use the previous technique. We have to use a new one. Because this is an exponential, we undo exponentials with their inverses, which are logarithms. So what I'm going to do is take the log here first. Probably should rewrite that. Here, I'm going to rewrite the equation here. 5x. Sorry, guys. Let's just erase and start over. Oh. Okay, so let's rewrite it. 5 to the x minus 2 equals 200. And then I'm going to take the log of both sides. Because what you do to one side, you have to do to the other side. And then on the left-hand side, I can use the power property. I can take the x minus 2 out front. Times the log of 5 equals the log of 200. And then I am solving for x. So so now what I can do is I can divide both sides by log of 5 or log 5. Because log 5 is being multiplied to x minus 2, so we can undo it by dividing. That cancels that out. And so you get x minus 2 equals log 200 over log 5. And then you just have to add the 2. So x will equal all of this over here, and then we'll go to our calculator, which I have to bring up. And we'll put that in our calculator. And the log is base 10, so that's on the calculator. All right, so we're going to do log 200. We have to close the parenthesis, divided by log 5, close the parenthesis, hit enter, and then we can add 2. So 5.292. And that's actually an approximation since I had to round. And then to check it, 5 raised to, and I'm going to plug in the 5.292 minus 2. Does that equal 200? So back to the calculator. 5 raised to 5.292 minus 2 is going to be 3.292. 199.99. Well, that's pretty darn close to 200. We have a little rounding error because I had to round the x when we answered it. So yes, we can be confident that this is our answer. There is another way to do this problem if you don't like the way I just did it. Let me just show you this so you know. You can choose. Oops, we'll do green. Okay, this is another method, method 2. What you can also do, I'll give some space here, is because this is an exponential base 5, you can take log base 5 of both sides. And on the left-hand side, once again, so what I did is I took log base 5 because the exponential was base 5. And then on the left-hand side, we can use one of the inverse properties that says these will cancel out, and you're left with x minus 2 equals log base 5 of 200. And then add the 2. Both of these methods we use about the same amount. I mean, they're both very valid methods. And now let me show you. So let's remind ourselves again, the log base 5 at 200, we don't have a key on our calculator with log base 5, but we can use the change of base formula that we learned in the previous section. And that's going to be log of 200, because 200 is the upper one, over log 5 plus 2. And guess what? That's exactly what we got with the other technique as well. So obviously it's going to be the same answer. It's just a slightly different approach at the beginning. So instead of taking log of both sides, you could have taken log base 5 of both sides and got the same answer. Okay, these try on your own, and then I'll be doing them. So this first one, I would say we could rewrite those both with a base of 3. The left one is already base 3. And then 3 to the third is 27. Now we have identical bases, so we know the exponents have to be identical. Divide by 2, and we get 3 halves. We're going to check it. 3. So when you check, go back to your original. 2 times 3 halves. So question marks, it's a check. 2 times 3 halves is the same as, these 2's cancel, that's the same as 3 to the third. Yeah, 3 to the third is 27. So we did it correctly. On this one, you can't write 21 with a base of 7. So you get to take your pick. If you want to take, you could do log base 7 of both sides, or you can do log of both sides. I don't know which one you prefer. I really don't have a preference one way or the other, so I'm just going to choose just the log of both sides. So the negative x can come out front using the power property. Then we get to divide both sides by log 7 to isolate the variable x. That kills it. And we can get rid of the divide by the negative, so change that to a plus and change that to a negative pretty much. And then we go to our calculator. Whoop. Clear that. So we're going to have log of 21 divided by log 7. Whoops, I don't know why I hit x. Okay, and that's going to be, then it's going to be negative because there's a negative at, whoops, come back. 1.565. Oh, okay, bathroom thing. Let's check that. So 7 to the negative, because it's a negative x, and the x is negative, so that's going to become positive. On our calculator, let's see what that equals. 7 raised to 1.565. 21.02. Close enough to 21, so it's approximately 21, so it does check. If you don't want to take log of both sides, you can take log base 7 of both sides. Example 2. You can choose a prize of either a $20,000 car or 1 penny on the first day, double that to get 2 cents on the second day, and so on for a month. On what day would you receive more than the value of the car? Well, I was going to ask you which option you would choose, and if you're familiar with that question about the king and the chessboard, where you put the grains of rice, 1 grain of rice on the first block, 2 grains on the second, you realize, if you're familiar with that, that by the time you got to the 64th square, there's not even enough rice in the world to account for what would land on that square. So, yes, it's going to be smarter to choose the 1 penny on the first day. In order to come up, we need to come up with an equation. And this one's a bit tricky, so I'm going to make a table. The day number, the day, and the amount of money in cents. So on day 1, you're getting 1 penny. On day 2, that doubles to 2. On day 3, that doubles to 4. On day 4, it doubles to 8, and so on. And because we're doubling, it is exponential, so it's going to be y equals a times b to the x is going to be our equation. A stands for the initial amount. The initial amount is 1 penny. That's 1 cent. And we are doubling, so the base is 2. Now, this is where it gets tricky. If you put x here, x is the day. And then, so you might think, okay, this is the equation. But if you check it, you're going to see something interesting. So on day 1, if I put y equals 1 times 2 to the 1, what am I going to get? I'm going to get 2. And if I try day 2, so I'm going to call that y sub 1 for day 1, and let's call this y sub 2 for day 2. So if I go back to my formula, 1 penny, I should put units on here, times 2 to the day 2 is 2. You would get 4 cents. Well, on day 1 we should be getting 1 cent, and on day 2 we should be getting 2 cents. So this equation needs to be adjusted a little bit because it's giving us the next one instead of the one we want. And the way to adjust this, if you haven't figured it out already, is if we subtract 1, we need to subtract 1 from the x. Because if we do that, let's test it that way. So over here, 1 times 2 to the x minus 1. If you try day 1, so y sub 1, you would get 1, 2 to the 1 minus 1. That's 1 times 2 to the 0, and 2 to the 0 is 1. And that's what it should be, because on day 1 you should be getting 1 cent. I doubt I'm going to ask you to come up with an equation like this on your own, because it is tricky. So anyway, the equation is that we have to do x minus 1. So now I'm going to erase all this other stuff, now that we've got our equation. And we can do the problem. So it says, on what day would you receive more than the value of the car? Well, the car is $20,000. So how many cents is that? I want to keep everything in cents to keep, I think it'll be easier that way, since this side isn't, this is in cents. Well, there's 100 pennies in a dollar, so you need to multiply 20,000 by 100, or in other words, add 2 zeros to it. So 2 0 0 0 0 0 0. So that ends up being 2 million pennies. 1, I really don't need the 1, you can drop the 1 if you want. 2 to the x minus 1. So I'm going to come down and write it without that 1 there, because you don't need that 1. Okay, so now we need to solve this. Just for fun, I think I'll do this one by multiplying or taking log base 2 of both sides, so that you can get familiar with both techniques. So I'm going to do log base 2 because the exponential is base 2, and log base 2 will undo it. So over on the right, these knock each other out, and you're left with x minus 1 equals log base 2 of 2 million. And so on our calculator, we're going to use change of base formula, by the way. So that's because we don't have base 2 on our calculator. That's log of 2 million divided by log of 2 equals x. And you know what? I'm going to add the 1 over while I'm at it. Why not? So we'll add 1 to both sides, and then we get x on the right-hand side. Okay, so now we'll do log of 2 million, 2, 3, so that's 6 zeros. Close parenthesis, divided by log 2. You can hit enter there, and then we're going to add 1 to that. 21.9, so about 22 days. So on day 22, you will have more than the value of the car. Okay, let's go on next. Okay, now we have logarithmic equations. So before we had exponential equations and we took the log to undo them. Now we have logarithmic equations. We are going to use exponentials to undo them. And it's called exponentiating. And in this case, because it's log base 3, we're going to exponentiate base 3. Exponentiate base 3 is what it's called. And what it looks like is you're just going to make the 3 be the bases. And so you get this. And the nice thing about that is you can use your inverse property. The 3 raised to the log base 3 undoes, and you're left with x minus 5 equals 3 squared. X minus 5 equals 9. Add 5 to both sides. X equals 14. Now you do have to go back and check. Log base 3, I'm plugging 14 into the original equation and checking to see if it equals 2. So this is log base 3 of 9. Does that equal 2? Yes, 3 to the second power is 9, so it does check. Okay, this one on the right, slightly different technique. We are not able to exponentiate both sides right now, and the reason is on the left-hand side you have a difference. You can't exponentiate both sides until you have one chunk on the right and one chunk on the left. So what we need to do is we need to get the left-hand side, we have to actually condense it into one logarithm. And we can do that by our log properties. The difference of logs is the log of the quotient. So this is equivalent to log of 45x over 3 using log properties. And then 45 divided by 3 simplifies, so that's 15x equals 1. And then at this point, actually you have a couple ways you can solve this. You could just, because this is log base 10, you can just rewrite it in exponential form. That's the same as 10 to the 1 equals 15x. Divide both sides by 15. And that's, that's 2/3. That's one way to solve it. Another way is, okay, let me go back to blue color here. We had log of 15x equals 1. That's base 10. So what you can do is you can exponentiate base 10 to both sides like that. And then that knocks that out of there, and 15x equals 10, and you'd get the same thing. You're going to divide by 15 and get 2/3. So on one of them, on this one, I decided to just change this from logarithmic form into exponential form, down here. And then on the other technique is to exponentiate both sides base 10. You end up getting the same thing. Oh, we do have to check, super important, because, well, you'll see here on some of these. So I'm plugging the 2/3 back into the original one. So that's 45 times 2/3 minus log 3. We can simplify this because 3 will go into 45 15 times. 15 times 2 is 30. The checking is almost taking as long as figuring out the problem. This is the same as, because we're subtracting, it's the same as log. It's not going to write for me now. Too close to the bottom. Oh no. Look at that. It rewrote my, that's funny. It rewrote things. Okay, let's go back. Okay, weird. Shoot. Okay, here we are. So I'm going to come up here where I have some more room. 30 over, so that rewrites as log of 30 over 3 equals 1. That's log of 10, or log 10 rather. And yes, that's true because 10 to the 1 is 10, so it checks. So we're okay with this answer. Try these on your own. Okay, on this one, I'm going to exponentiate base 4 to both sides. So that's going to knock that out of there. X squared equals 4 to the 7th. I'm going to take the square root of both sides, plus or minus. So plus or minus the square root of 4 to the 7th. Whoop, calculator. Second square root of 4 raised to the 7th. 128. Plus or minus 128, because whenever we take the square root, we need plus or minus. Let's check it and see if it works. Log base 4 of 128 squared. I'm just going to put that in the calculator. Oh, well, we better, here. Let's do 128 squared, because we need to know what that is. Okay, that's 16384. Then I'm going to check that using change of base formula. So that's the same as log of 16384 divided by log 4. And that's 7. That's good. It should be 7. And negative would give you the same thing, because if you put a negative in here and squared it, you'll get the same answer. So we end up with 2 numbers that make that true. On this one, we need to get the logs together on the left, and they're being added. So that means it's the same as the log of their product, x times x plus 9 equals 1. So I've just used one of our log properties on the left to get it into a single logarithm. Now, it's base 10 because it's a common log, so I'm going to exponentiate both sides base 10. It's going to knock that out of there. Oops, not the x. The x is still there. It just knocks out the 10 log base 10. Sorry, got a little overzealous there. And then we can distribute. And while I'm at it, I'm also going to subtract the 10 over and get it on the left-hand side of the equation. And then there's a 0 on the right-hand side. So I distributed, and I also subtracted 10 to both sides all at once. This we can solve by factoring. We can try 2 sets of parentheses. X and x will go here. 2 numbers that multiply to negative 10 and add to 9 would be positive 10 and negative 1. So that means the answers, when we set each of those equal to 0 in our head, we get negative 10 and positive 1. So we're also getting 2 answers on this one. We need to check it, so I'm going to erase what we've got over here. And this is the check. So I'm checking in the original. Log of negative 10 plus log of negative 10 plus 9 equals 1. Question. Okay, let's go to our calculator. Let's do log of negative 10. Can you think of what that would be? 10 to what power would equal negative 10? Okay, if you can't think of anything, that's because there isn't an answer. Because check this out, log of negative 10. There's an error. It's because you can't take the logarithm of negative numbers. So what this means for us is that negative 10 is not a solution, because it won't work. It's not in the domain. Let's try 1. Checking 1 in the original. Log of 1 plus log of 1 plus 9, which is 10, equals 1. Question. we could do this in our head. 10 to what power equals 1? 0. 10 to what power equals 10? 1. 1 equals 1, yes. So we do have a solution of 1. So this negative 10 is called an extraneous solution because it's produced in the solving process, but it doesn't actually work in the original one. So you can get extraneous solutions when you're solving logarithms. That's why we have to check them. Okay, these are, looks like they're more of the same thing, so you can try them on your own before you watch the tape. Okay, so what I've got here, on this one I've got 3 log x. I want to put that 3, because what's going to happen over here on the right hand side, we need to combine these logarithms and get them together. And we can't do that. We can't use the addition property when there's a 3 out front here. So we need to put the 3 up. We have to use the power property and move it up into the exponent there. Now we can combine them using the addition property. So because they're being added, that's going to be the log of their products, 8x cubed. And now we can solve it. It's log base 10 again, because it's a common log. So I'm just going to exponentiate base 10. So I've got 10 to the third, which is 1,000. Just write it as 10 to the third. And then there's a base 10 here. This part cancels, so you're left with 8x cubed. So this is 1,000 equals 8x cubed. Divide both sides by 8. And then to undo a cube, you do a cube root. Like so. And you're taking this whole side, the cube root of that entire side. Oh, guess what? Because this is a division and they're both under the cube roots, you can rewrite this as the cube root of 1,000 over the cube root of 8. And I want to do that because I can take the cube root of both of those. What number do I multiply by itself 3 times to get 1,000? And the answer is 10. What's the cube root of 8? 2. 2 times 2 times 2 is 8. 10 divided by 2 is 5. That equals x. When you take the cube root or the fifth root or any odd root, you don't do the plus or minus. So we just have x equals 5. Let's check that. So 3 equals log 8 plus 3 log 5. You can just type that all in your calculator. In fact, let's just do that. Why not? We'll type the stuff in on the right, so clear all that out. Log 8, parenthesis, plus 3 log 5. 3. You could have also checked it by simplifying it by hand, but I thought, why not? We'll go with the quick route. Take the quick route. Great. Okay, so try this one on the right on by yourself. Okay, this one's similar to the other one. Actually, on this one, yeah, this 2 out front here, we cannot use the difference property until the 2 is up, becomes the exponent there. So we have to do that step first. Has to be done first. Now we can use the difference property. So that's going to be the quotient of those. You're going to divide those, x squared over 4. And we just have 0 on the other side. And this is a common log, so we're going to exponentiate base 10 to undo it. That kills that. You get x squared over 4. 10 to the 0. 10, anything to the 0 is 1. Multiply both sides by 4, because we're going to solve for x squared. Take the square root of both sides. It's an even root, so you do need the plus or minus. However, what happens when you go to plug negative 2 in here? Can you take the log of a negative number? No. So actually, negative 2 is not going to work. So only 2 will probably work, and let's check it and find out. Again, let's use our calculator. So let's do 2 log 2 minus log 4 on our calculator and see if we get 0. 2 log 2 minus log 4. Enter. 0. So x equals 2. And this, because we're using tables and graphs, we're going to be using our calculator strictly instead of doing it by hand. This one you might be able to figure out already if you know it. Anyway, let's just do it. So on a calculator, one way of doing this problem is go to y equals, and we could make 1024 be one of the equations, and 2 raised to the parenthesis, 2x, is the other equation. And we want to know when these equal each other, so we're going to look for where they intersect. Now, 1024 is a horizontal line, so I know in my window I need to have my y max has to be bigger, at least 1024. I'm going to make it, I don't know, how about 1500? You don't really have to make it that big. Maybe I'll make it 1100. And the x's I might need a little more than 10. I don't know. We'll see. Let's try 20. Let's see what happens if I graph it. Oh, good. So where they intersect is where our solution is going to be. We find that by doing second trace, intersect, enter, 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 and it's when x is 5. So we used a graph to do that. It does say use tables as well. So we can use the same thing. I've got one of them in y1, one in y2. You could set your table. I've got it starting at 0 and counting by ones. And you can look in your table and look to see when the two equal each other. And that happens when x is 5. Okay, on this next one, you are looking for where the left-hand side is less than or equal to the right-hand side. You can type it in how it looks, or you could use a log property and simplify it first. It really doesn't matter, so I'll just type it in the way it looks. Log of x, make sure you put a parenthesis there after the x, minus log 2. And then in y2, I'm going to have log of 75. I can try my old window. I don't know. I'm just going to quick press graph. Yeah, that's not a good window. I'm going to start with Zoom 6, a standard window. Okay. And I can see that these are pretty flat. It looks like they're not going to cross until the x is really, really large. So I'm going to make a really large x, like 1,000. That might be too big. Let's see what happens. Oh. Yeah, that's a little big. I think I'll tone it down to 500. The other thing I'm going to do, because these are close to the x-axis, I'm not going to make my y max. Actually, I'm going to make my y min and my y max smaller. There, that's nicer. And the other thing you can do, well, let's find out where they intersect. So second trace, intersect, enter, enter, enter. They intersect at 150. But because this is an inequality, you have to figure out, is it less than or equal to 150, or is it greater than or equal to 150? And what you can do is you can trace and see. Okay, so on this curve, on the curve part, that's the left-hand side of the equation. When we want to know when the left-hand side is smaller than the right-hand side, so this is the left-hand side, when is it less than or equal to the right-hand side? So we need to know when this curve is less than, below, down here. So it's going to be everywhere where x is less than 150, less than or equal to 150. Now technically, it's actually greater than 0 too, because that logarithm can't be 0. I wonder if the book was real picky about that. I'm going to check and see just out of curiosity. Oh, they did. Yep, they did consider it. So because your x's can't be, you can't take the log of a negative. It has to be greater than 0. I was also looking to see if they did it. They did do it with algebra, and you know, that's not a bad idea. We could do that. I'll just do it really fast. So if you want to check it with algebra, You can use your properties. That's going to be a quotient because you're subtracting. Keep that inequality symbol. And then we're going to exponentiate base 10. So x over 2 is less than or equal to 10. Oh, look at that. This is going to also simplify out. So that's actually 75. And then multiply both sides by 2, and you get x is less than or equal to 150. It's almost faster doing it than doing it on the calculator. And then you'd have to recognize that it has to be positive, so greater than 0. Okay, I'm just checking. Okay, so this is our last slide. A couple practice problems for you to try on your own. And this is on a calculator. So, of course, I just want to jump right in and do it by hand because it'd be so much faster. But anyway, it does say to use tables and graphs. Okay, we got 2 to the x. I'm going to try to go fast. I'm running out of time. And then 4 raised to the parenthesis x minus 1. Let's try zoom 6 to start it. Okay, great. And then we're going to look for where they intersect. 1, 2, 3. They intersect when x is 2. Let's check that. 2 squared, does that equal 4 to the 2 minus 1? 2 squared is 4. That would be 4 to the 1. Yes, it checks. Second one. Oh, this is really similar. So, I have to think for a second. How do I do this so damn fast? Okay. 2 to the x is greater than 4 to the 2. X minus 1. So on this one, when you solved, you would have gotten, what did I do with my work? Oh, I did it on the calculator. All right, never mind, guys. Okay, I was going to do it by hand real quick, but I'll just do it on the calculator. Why not? That's the way they said to do it. Okay. I'm going to trace, and I'm going to just move along a little bit so I can see which curve is which. Okay, so they want to know when the 2 to the x curve is bigger than the other one. And right now I'm on the 2 to the x curve. And where my cursor is, it's smaller. So it's going to be greater down here when x is less than 2. And you can do a check. Pick a number less than 2. So 1. 2 to the 1, is that greater than 4 to the 1 minus 1? 2 to the 1 is 2. That's 4 to the 0, which is 1. So yes, that checks. And we're done.